be a short class.
Understood, sir.
All right, so all right. So today we are going to talk about these three and so I usually just talk about these things or most things by working out a problem. So um so let us so that we have this vector surface and x squared I plus x y z j plus y squared k. And we want to find the tree. So we want to find the gradient function of it. We want to find the divergence of it. I want to find all right, so first thing that we need to do is define the operator. So I'm going to define what I call a del operator. As so the del operator is an upside down triangle. So we are saying that this del operator, we are going to define it, and then that will help us when we're defining. So it's a partial derivative with respect to x of I, partial derivative with respect to y of j, partial derivative with respect to z of k. So the definition of the gradient is equal to del operator of my function f. So if I have a function and the gradient is given by, so therefore, we are going to put in the operator in this. So grad f would be derivative of the function with respect to x, I, the derivative of the function with respect to y, j, plus the derivative of the function
Sir,
with respect to z. Okay.
Oh, what is that? Beside starting below the definition, is that a bracket?
So let me out. All right. So yeah, I was just saying that when we say del f, we're going to fill in the f inside of the function.
Wait, sir,
Oh,
so
So the gradient,
wait, sir, are those twos or are those?
no, the the operator.
Oh,
is
Yeah, partial derivative.
we call it curly D. I call it, well, I've heard it called
Curly
curly
D.
D. It's like dy by dx. So curly D, y by curly D. X. It's still a D, but it's a curly D. Partial derivative. It doesn't look like a D, but it's supposed to be a D. All of these things are D's. This,
Or
this,
sir.
and this. It's also supposed to be a D. The Greek letter D.
Right, sir, we can use MATLAB on the partial
There you
different
go.
derivatives.
You should be able to, yeah.
Because it's that what I was trying to figure out the other day, but I couldn't really catch it.
Well, we can show you. Well, we show you how it.
Sir,
You have to use it. Huh? Yes.
since you're applying the del operator, the last line you wrote, since you're applying the del operator, why you never just put the partial derivative instead of writing del f?
Sorry, it's not part. It's not del. It's supposed to be the partial. Thank you for that correction. Stupid is not just right. This that is supposed. This is what it's supposed. So we are to step. So this is the function that we are working with here. So the gradient. Sorry, 1 second. So the gradient. We're going to take the derivative with respect to x of the function. We're going to take the derivative with respect to y, and we're going to take the derivative with respect to z. So what is the derivative with respect to x?
Sir,
2x.
2xi plus y z.
Sir, would not be 2xi plus x.
Plus yz, sir.
All right,
Y.
so
Yzj.
yz,
Plus j.
equation with x is 1, so it's yz j, and with respect to, there's no x here, so there's
Y
nothing to
squared j.
differentiate.
That will
So
be
therefore,
0.
what about the derivative with respect to y? There's no y here, so that would be
0.
0. Where we
0.
differentiate y here?
X, z. Xj. Plus 2y.
2yk.
0 plus xyj.
XY.
So xyj
XYJ.
alone. Plus 0.
There's nothing here. All right. Did the wrong thing here when we are, well, normally the function we consider it without the I and it. So the derivative with respect to x, we're just going to write it as 2x plus yz. Derivative here is xz plus 2k, and the derivative here is xy. So our gradient,
So it would be 2k or 2y.
2y. Brain not here this evening here. J plus x, y, x, y. Okay, that would be what the gradient would look like. So the gradient would be the derivative of the function with respect to x, y, and z. All right, and so, well, let me deal with what to use it for. Just dealing with the mechanics right now. All right. So what about the divergence? So then we can go on to that.
Divergence cross product.
So the gradient, the divergence, no, is it that product?
Yes, sir. And the curl is the cross product, right?
And the curl is a cross product. And the curve, like I said, now, all right, so let's
So the K would not be
just
involved in the
deal
equation,
with the
sir?
mechanics. No man, I'll keep on leaving off the K.
So let me get this right, sir. You can
No.
get all that from just that end part down there.
And again,
You can get the answer for all three of those just from the equation that we got down there.
this
Yeah, from that
here,
equation. Yes, sir.
if we can get all three answers from this down here.
I think he's mentioning the fact that because each one of them includes the partial derivative f of x, partial derivative f of y, partial derivative f of z, that once you calculate grad f, we have piece of the puzzle to solve div f and curl f.
So just
Fortunately, no.
no.
Yeah,
Because the divergence now is going to be the dot product. So we're going to take the dot product of each of these. So it's not the whole entire derivative we're going to take now for the divergence. It's just the first one we're going to differentiate with respect to x, second one with respect to y, and third one with respect to z. But let me write it down.
Okay.
Can I go to the next page?
Yes, sir.
One sec, sir, one sec.
One sec, one sec.
All right.
Yes, sir, you can move on.
All right. So so if we let x, the function, be equal to something I, sorry, if we take the dot product, then remember when we had vectors like, then the dot product was taking these two, multiply them, and then add them, and then added them together. So if we take the dot product of the cross product, then what we're going to end up with is we're going to differentiate the first term with respect to x, the second term with respect to y, and the third term with respect to z. So this is my definition. So if we go back to the function that we had overlaid, I didn't write it down. Give me a second, let me write it down. So that is x squared I plus xyzj plus y squared k.
Sir, we're not hearing you, sir.
Sorry, I was dealing with some domestic issues. So, okay, so we're saying that if we had the function that we had before, then if we differentiate the first term with respect to x, that would be 2x I. We're differentiating the second term with respect to y, that would be x, z, j. I would differentiate the third term with respect to z, that would be, I would put plus 0. So therefore, this will be 2x I plus x z j.
Sir,
Mhm.
when you say first, second, and third term, you mean the I, J, and K terms? Because what if you have only two terms? For example, I and K.
Then the second term is equal to 0.
Okay.
All right. So that is divergence. So what about curve?
Sir, 1 minute before you move on, sir. We have, what's this now? Del, the F, you have 2xi plus, what's the,
Differentiate in respect to y.
And for the last term, you differentiate
So
in
when you
respect
differentiate
to,
y, z,
oh, in respect to z.
there's
Okay,
no
sir.
z there, so
Also differentiate them each with their respective
yeah, right. In the original function, we differentiated the whole function with respect to x, whole function with respect to y, the whole function with respect to z.
Sir, shouldn't there be like a like as we have a x square I, a x y z j, y square? Kind of confused. Sir.
I'm kind of confused too.
All right. So f1 is equal to x squared. That is what is in front of the first one. The second one, f2 is equal to x, y, z. And in the third one, f3 is equal to y squared. So if we're going to differentiate now, differentiate the third one with respect to z, you're going to get 0. Differentiate the second one with respect to y. When differentiate y, you get 1. Is going to be equal to x, z. And differentiate the first one with respect to x. That's just 2x. So that's why we're saying now that that is going to be equal to differentiate the first one with respect to x and second one with respect to y. Second term in the function. If there's no second, if the function with the j function, part of the function is not there, then you write 0 for whichever one of it. And we differentiated the third one with respect to k. So we'll put that together. That's why we get the 2xi plus xzj plus 0. So we're taking each term and we're going to differentiate the first one with respect to x, second one with respect to y, third one with respect to z. Now, if we had the function in the first instance, when we said differentiate, we differentiated everything.
Mommy.
Right.
Your mic is on.
That's why my finger must be on the mute button. All right, so is the first term in the expression that we're going to differentiate with respect to x, second term with respect to y, and the third term with respect to z when we're finding divergence. All right, so as opposed to when we're finding the gradient. We're just differentiating the whole function, not term by term, but the whole function. I don't know if that makes it any better. All right. So can I talk about curl? I can move to the next page.
Yes, sir.
Yeah.
All right, so curl is the cross product. So, and we know that for the cross product, we put I, J, and K, and is the partial derivative with respect to X, partial derivative with respect to Y, partial derivative with respect to Z. First, second, and third part of the function. So, prefer to leave it like that when and not write out the whole entire I, you differentiate F3 and then minus it from F2 and all of that long term. This is a more compact representation. So we had F is equal to X squared I plus XYZ J plus Y squared K. So, and we said that this was F1, this was F2, and this was F3. So, in this particular is going to be I, J, K. So this is X squared, this is X, Y, Z, and this is Y squared. That determinant. So that would work out to I. So it is partial derivative with respect to Y, partial derivative with respect to Z, and it is X, Y, Z, Y squared, minus J, derivative with respect to X, derivative with respect to Z, of X squared and Y squared, and it's K, derivative with respect to X, derivative with respect to Y, of X squared and XYZ. All right, so now it's I. And then we're taking the first going across. So we're taking the partial derivative of Y squared. So the partial derivative of Y squared is going to give me what? Can differentiate Y squared, what you're going to get?
2y. 2y, sir.
2Y. And then 2Y. And
That's
then
a
we're taking
minus
the partial derivative. That's minus. We're taking the partial derivative of XYZ with respect to Z. We differentiated the Z and we're leaving the rest alone.
XY.
So that is going to be XY minus J. We're taking the partial derivative of Y squared. So that's 0. zero. When we take the derivative, there's can't differentiate. And the same thing, partial derivative of x squared with respect to z, that's zero as well. And then plus k, partial derivative with respect to x, when differentiate x in this, you get 1, and then yz is left. And the partial derivative of y with respect to y of x squared is going to be 0. So therefore, it's going to be 2y minus xy I. There's no j, and plus yz here. So we just want to talk about this a little bit. Why all of this? What all of this is for? So let's just everyone I can move to trying to put some context to all of this.
That's why I can move on.
All right. So an electromagnetic wave. The last term is the term that we think we understand in engineering, and the first two most of the time don't make any sense. But the last one is the one that we want to talk about, because we need to, when we're talking about a wave, what is a wave?
An urban flow, urban cursor.
All right. Yeah. So just tell me what it does. Which are how it moves. But what
movement of energy through a medium, sir.
if you're the essence of a wave? Huh? All right. So a wave allows energy to be transmitted without the actual movement of the source. So, for example, you know on planet Earth. You're on planet Earth. This is the sun. Is the sun hot?
Yep.
That was a question. How do you know? Have you ever been to
Because
the
of the
sun?
change in temperature.
The
Because of
waves, the waves, heat waves.
radiation wave, the
So-
radiation wave.
You directly know that the sun is hot because you have felt the heat of the sun, right? So let me ask a different question. Is New York cold?
It's not always cold.
Not always cold. Is it cold now?
I wouldn't know because I'm not feeling it.
You wouldn't know because you're not feeling it.
Yeah.
And you'd have to be there. So you'd say you'd have to be there or ask somebody who is there to tell you whether or not New York is cold. But you don't need anybody to tell you that the sun is hot. Because you are on Earth experiencing the sun. So whenever energy is transmitted from a source to a point, that energy, the source don't move, the sun is not moving, and you are here and you are directly experiencing that sun, then we say that that energy is transmitted as a wave. And that is the basic definition of a wave. So use another example. This is a water surface. Here's a leaf. You throw a stone in the water here. The leaf will start moving up and down. It didn't throw the stone at the leaf. You throw the stone at a different point, but the leaf starts moving up and down because the water surface from the source spreads to the leaf. So that energy, again, the motion of the leaf is kinetic energy. That energy is transmitted via a wave. Now, the wave with the sun is, there's no material medium, but the wave with the stone thrown in the water, there's a material medium. Here, there's no, the sun, there's no material medium. When there's no material medium, we say that it's an electromagnetic wave or EM wave. So what if I have a charged particle? So let's talk about an electromagnetic wave. And there's another charged particle. If the two like charges are there, what is going to happen to these two particles? If you have
They're going
two
to
like,
repel.
they're going to repel. So they are going to want to move away from each other. So suppose this one is now oscillating. This one is going to be, is in the field, the region where the force is experienced. So this charge is now in the field of this oscillating charge. So it will also experience a force, but that force is varying. You would agree? As the charge moves away, the force is less, and as the charge moves towards, the force is more. So it's going to experience a varying degree of force as the charge moves to and fro. Do we agree with that?
Yes, sir.
So we say discharge then it causes discharge to oscillate as well. Now, a moving charge is called a current. So a charge that is in motion is called a current. So if we have a current that is behaving, a set of charges that are moving in one direction and moving in the next direction, then what they are going to do is any other particle that has charges, it's also going to have an effect on them. So that is our thing with our radio station and with the antenna. So there's current flowing, and so if there's another antenna in the vicinity, in the field, then the current will also cause current to flow in that one, and then we can decode it, the signal, and so forth and so on. But there's another thing that we just want to point out, that when we have a charge that is moving, it will also cause a force perpendicular the charge not to move in a straight line, but if this charge is moving towards this charge, then there are two forces in operation. There is a force due to the electric field, and then the perpendicular force, that is force due to the magnetic field. And every charge that is in the magnetic field and the electric field are perpendicular to each other. Now, so I'm trying to put a context to this. So if the electric field is the magnetic field is perpendicular to the electric field, then remember that we have been saying that when you find the cross product gives you a vector that is perpendicular if the cross product gives you a vector that is perpendicular to the vector in question. So
and that vector
so
would be the
if
surface
my
area, sir?
and
Yes, it
that
gives
vector
a
would be the
I asked if it would be perpendicular. Yes, perpendicular to the vector. Is the vector with the surface area?
right.
Okay.
Right. So perpendicular to the surface here. So if I have a charge and the charges are on the surface, for example, it's fine if the charges are static, so it's one static charge. But suppose they are increasing and decreasing, and I want to find out perpendicular to this surface, what are the electric and magnetic fields experienced? Then I'm going to have to find out, first of all, an equation for the charge on the surface, or the voltage are on the surface. And then I'm going to have to find, I'm going to have to take the cross product to find the perpendicular to the vector perpendicular to the surface. So at that point, so we can use the cross product to find a vector that is perpendicular to the surface. Now, so whenever we describing electric and magnetic fields, you will see the cross product being used a lot, or you will see curl being used a lot, because the magnetic field is always perpendicular to the electric field. And if a charge is in motion, then that charge will have two fields associated with it. The one that, if we're just taking the x direction alone, then there's going to be an electric field associated with it. And if we take the perpendicular, that's the magnetic field associated with it. So if there's a moving charge, which we call a current, once there's a current, there's always going to be an electric field and a magnetic field associated with that particular current. Now, usually, like I said, just building a case. So usually, if we just take the x direction alone, then usually that we usually describe, let us say that is the voltage due to an oscillating charge. Then that is usually some with respect to t in the x direction. But suppose we are not dealing with a charge just going in the x, a charge influencing the x direction. Suppose it's also influencing the y direction. So we are going to say that is plus some b, and let us say that it is cos omega t j. And there's also going to be a z direction influence as well due to the charge, plus some c, put a phase angle on it. So we are saying that the voltage is usually, if we are trying to capture the voltage in 3 dimensions, then it usually is, if it's oscillating, then we are going to be talking about it going in three different, we're going to be describing it in 3 dimensions, the I, the J, and the K, X, Y, and Z direction. Now, and I'm saying that the voltage or the potential is going to be in that direction. Suppose I want to find the force. Well, let's say force is equal to rate of change of voltage with respect to the displacement. Sorry. But, so that is what they would tell you, that force, if you have a, if there's a field, so there's a charge, it's causing a force. So that force that we're talking about, it is causing a force, and usually when we talk about voltage, is that we talk about work done. I'm getting too technical, I'm getting too much into other people's business. So let us say that you have this charge out in the field and you have this other charge here. And this thing is at a distance x. We usually have a relationship that says the amount of work that I need to do to carry this charge from this point here to another point. We usually call it potential or voltage. But if I want to find the force, then the force is usually taking the derivative with respect to. So now, I have this big formula for voltage in the x, the y, and the z direction. If I want to find the force due to this charge, then I'm going to have to differentiate this. So which one of the derivatives am I going to look at? Is it the curl, the divergence, or the gradient? Because if I have a representation for the voltage in the 3 direction, the potential in the 3 direction, and I want to find the force in the 3 direction, then I'm going to have to find things like the divergence, differentiate each of them in the x, y, and z direction to find out what is the force in the x direction, what's the force in the y direction, what's the force in the z direction. And then I put it all together and say the force is equal to something. If I find differentiate with respect in the x direction, differentiate in the y direction, differentiate in the z direction, then I would be able to tell you what the force is in all of those directions. So this A is not necessarily a constant. This A can mean that in the x direction, the charge is doing something like this, or more typically is doing something, all different kind of things. So you might end up with x squared, 4x squared, yz or something as my a. I have to differentiate that to find the force. Or I might have to integrate it if I have the force to find the potential. If I want to find the magnetic field, then I'm going to have to find the current, meaning that I'm saying that this is the potential, this due to the charge. What about the magnetic field, which is perpendicular? How do I find that? Then I have to find a vector perpendicular. So that is why we have to take the curl and those kind of things. So like I said, I was just trying to give a context in which we need to have these kind of relationships and what it is that we need we are doing when we're finding these relationships. The curl and the divergence and the gradient have to do with electromagnetic waves. Most of it in engineering, most of the time it have to do with electromagnetic waves, and we're finding vectors that are perpendicular to represent the magnetic field, and how is it that the vector is related to the electric field and those type of things. And we are dealing with in three, well, actually, scientists will tell you four dimensions. Yeah, what are the four dimensions?
Three spatial and one time. Sir, I want to answer something, sir.
Then flip the one time.
And this thing can be moving. Time. Yeah.
Sir, may I try to get the intuition of the curl and things, sir? Because when you do like electromagnetics, them tell you like them say the curl is when, like is the point, like them say the curl of the magnetic field would are equal to like the electric field. But it describe how like something would rotate if you put it in the magnetic field. You get what I'm saying?
Yeah, because
right.
What is that if you not draw the line right? So because the electric field, so let me use a line to represent the strength of the electric field in the x direction. So you have an electric field in the x direction. And if it's field, just replace field by force. So you have an electric force in the x direction. And let us say that it is equal to the strength of the electric field is equal to x squared, for example. There's always a magnetic field associated with the electric field that is perpendicular. All right. So this magnetic field will always be perpendicular. There always is. So what they're saying is that the B is equal to usually are the electric field times the cross product of electric field and the magnetic field is usually equal to some value. We are saying that the two of them are always perpendicular. So the cross product, like we say, when you find the cross product of one vector, you're finding another. You're finding a vector that is perpendicular. So they're saying that the electric fields are and the magnetic field is usually when you find the cross product, they are telling you that the two of them are 90 degrees. We don't even remember the relationship. E cross B equal what again? It's not my big sphere. I don't remember the full formula. I don't know if anybody remember it from electromagnet. But all the point I'm making is that the electric field and the magnetic field are always perpendicular. Always perpendicular. So the cross product of one give the other. Cross product of one multiply by some factor give the other. So if we know the electric field in a particular direction, then all we have to do is find the cross product and we'll be able to say something about the magnetic field. I don't know if that making any sense. So if the electric field, strength of the electric field is x squared I plus xyj plus z squared k, then B is going to be equal to the cross product of this. You take the cross product of it and unit vector, and you will get B. B is usually some factor. Because they're always perpendicular. So once it's perpendicular, you're thinking cross product. All right. So those are some of the things that we all I'm doing is setting the stage to say that these are the reasons why we find curl and we find divergence and we find gradient. The other thing is that if you have a surface in space and it has, then what's the value of the force at that point? Then you're going to have to take the gradient with respect to x, y, and z to find the value of the force or the value of the current or the based on the relationships that we have, so that we can work out the values that are there. We look up the electromagnetic laws.
May I try to understand
I think it's
when
on.
Remember the law name again?
I think
glasses
I think the equation. Well, I'm not sure, but the equation I think you're looking for is like Lorentz force equation. But I'm not
Yeah.
sure if that yellow top out.
Yeah, this is what I'm looking for. Thank you. Lorentz force equation and the other equation. Those are some of the things that Tesla was. All right. So all right, this is an example of you would have been told at some point in your life. Oh, you would have been told at some point in your life that F is equal to EQ. I don't know if maybe you don't remember or don't care to remember. Not a problem. F is equal to charge times this E is the force of one charge. And this is the number of charges. And this here you were also told that F is equal to BQV at some point in your life. So B is the strength of the magnetic field due to one charge, but the charge have to be in motion for you to experience a magnetic. So what they're saying that this force is due to the electric field. And so the cross product telling you that it is perpendicular. And so it's perpendicular to the direction. The charge is moving in a direction with a velocity v, and the force is perpendicular. So it's v cross b. So you get the cross product that is giving you a vector that is perpendicular. So the EQ and the force is going to be the electric force is going to be in the x direction, and let us say that the magnetic field is in the y direction. All right. So, for example, that Lorentz equation is just trying to capture the force. This is the E times Q is a very simple notation. The force on one charge is E, and Q is the amount of charge that you have. So the total force is the amount of force on one charge times the number of charge. The BQV is a little bit more, we can derive it. But what all of this is trying to say, capture, is that you have a force in the x direction and a force in the y direction, and total force is some of the two of them, but is a vector sum, is not a algebraic sum. And so let me just say vector sum, differentiate between a vector sum and an algebraic sum. An algebraic sum say 10 dumpling plus 2 dumpling is 12 dumpling. And vector sum says 10 meters east and 2 meters west. Sorry, 10 meters north and 2 meters west. It's not 12 meters. You'd have to do a vector addition for that. So because the two things are perpendicular to each other. So you have to be able to differentiate between the two. Well, it wasn't Lorentz equation that I want.
My question was Maxwell
Three
equation.
lots. But anyway, all of that,
The question, the question I'm asking is related to Maxwell's equation. The curl and the
Maxwell equation.
And that, yeah. Because they do like the curl of the electric field and the curl of the magnetic field. Also a divergence of the electric field and a divergence of the magnetic field.
All right, we could try explain a little bit of what Maxwell was trying to do. All of this is in context of the same analysis. We find the expression of these equations written down somewhere.
The curl of the electric field is equal to the negative, if you remember, partial derivative of B over partial derivative of T. For the electric field. For the magnetic field, I don't remember.
Yeah, I want to write it out correctly. I don't remember the full, but I just want to give an explanation as to what they're trying to do.
Go back on it and go on images. Scroll up to images.
Oh, images, right.
Scroll up and then see images. All the way to the top. Yeah, and then click images and see.
Yeah, all right. All right, so now. So let me try and see if we can put a context to what Maxwell was trying his best to explain.
So some better one beside that, you know.
Yeah, use the
Which
next
one?
one.
Right beside the image. No, right that's it. Girl, but no, don't further.
Next one.
Right
This one, yes, sir?
Next, right beside that.
Oops. This one, yes,
sir?
Yes,
Yeah.
that.
This one here, sir?
Yes, sir, that.
All right. So what Gauss, the first law is Gauss's law, where they take the dot product. So what Gauss said, that if you take the electric field and need a paper. Need a, let me, I'll try right on the screen, but so Gauss was saying that if you take an electric field and you enclose it in a particular area. Let me write down the simpler law first, and then see if we can. So one of the laws that he did have is E is equal to Q over 4 pi epsilon naught R squared. So what he was saying is that if you had a charge and you surround the if you all right, let me see if we can. I want to put in the dot and the cross product and why we get one being equal to 0 and one we get it equal to.
Sir, because
all right.
see,
So
sir,
all right. We have to deal with dot product equals 0. Remember now, if we said that if we had two vectors that are perpendicular, the dot product is equal to 0. All right. So if we had a vector v1 and a vector v2, v1 dot v2 is equal to 0. Okay. That is one of the when we take a dot product. So basically this law is saying that if you have a magnetic field and you take any vector perpendicular to the magnetic field, right? Remember I said this here is the derivative of the magnetic field with respect to x, y, and z. We could use, so let us say that the magnetic field, for argument's sake, was x squared. But we can use now to explain. So when you take the thing perpendicular to the magnetic field, all that it is saying is that the two things perpendicular, you're going to get 0. If you try to capture the fact that if you take the grade, the divergence, which is the derivative of it, oh, we can put it. Give me a second. Let me compose it so that we can just put it simple and straightforward. I want to use the technical term.
Sure.
You can use an analogy, sir. You can use the source and sink analogy.
Yes, sir.
Is the perpendicular thing that I want to capture? Why is it that taking the dot product will be going to give us 0? That is what I want to capture. The third law is what I've been saying, that if you take the cross product of the electric field, then you're going to end up with the magnetic field. All right. The time is not that because remember I said this del deals with space. You don't deal with time. But this one here is saying that when you take the cross product of the magnetic field, then you're going to end up with the electric field. And this one says when you take the cross product of the magnetic field, then you're going to end up with the electric field, because all of these things are electric field. Give you the strength of the electric field. This J is charge per
current density.
But but all of this. So the last two, I just say when you take the cross product of the electric field, you get the magnetic field. When you take the cross product of the magnetic field, you get the electric field. one of them, the J is capturing the magnetic field along a line and so forth. Sometimes it is 0, and sometimes the other one is 0. But those two just saying the same thing. The two of them say the same thing. When you take the cross product of the electric field, you get the magnetic field. When you take cross product of the magnetic field, you get the electric product relationship because it's X and Y and Z. All right, but bear in mind, says an electric field and a magnetic field. So usually it has sine and cosine and tangent. I mean, sine something in terms of sine omega t and cosine omega t inside there. All right, so that's what these first two just said, that the electric field and the magnetic field are perpendicular. But I want to go back to the dot product equals 0 to kind of explain the dot product of the electric field and the magnetic field equals 0, and why the dot product of electric field is equal to typically a constant. This is typically charge. Okay. Remember I said that is a moving charge that has if you have a magnetic field, it's due to a charge that is in motion. A charge that is at rest is not will not have associated with it a magnetic field. All right. So it has to be in motion. All right. So if you have a charge that is in motion, then it will have a magnetic field associated with it. A charge at rest only has an electric field associated with it and no magnetic field associated. All right. So now, so let me deal with the first one. So we are saying that if a charge is at rest, you remember Coulomb's law? Anybody remember Coulomb's law? F is equal to K Q1 Q2 over R squared. Anybody remember that law?
Yes, sir.
Yes, sir. Where K is, I believe, 1 over 4 pi epsilon naught.
Right. 4 pi.
K. Electric field, E. What's the relationship between F and E?
Sorry, sir. Is that R square? Is that R square?
Yeah, R squared. Yeah.
Just making sure.
Yeah. So it's KQ1 Q2 over R squared. All right, what's the relationship between F and E? Well, we did say it earlier, F is equal to E times Q. So the force per unit charge. So if I take F and divide by the charge, then I get E. So I want the force per unit charge. And all Coulomb was saying is that the size of the force is directly proportional to the size of the two charges and how far they are apart. So that it was just capturing it intuitively, and came up with the equation, and then experimentally they came up with the value of the constant, which is 1 over 4 pi epsilon naught. So if you divide by, so E is equal to KQ over R squared if it is a charge. So I have to be writing and so if you have two charges and the distance is R, and this is Q1 and this is Q2, then we talk about the force. But if we're just talking about the force per unit charge, if this charge is 1, then we talk about E. Now, when we take, so this E is when we're talking about something in a straight line. But what about if it is a vector. All right, because we're taking a dot product, we're talking about X and Y and Z and the electric field in those regions. So now, this equation here and this equation here is related. This thing here is Q. This is charge. So now, how is it that I can put it so that when we get into electromagnetics, I know I shouldn't be, I should just tell yourself when you find cross product, this is how you find cross product, and this is how you find. I had gone too far into, I know we get myself into problems. All I wanted to say that this is why we take that product and this is why we take cross product. I know we got in a Maxwell's equation, which but like I said, the cross product one give you the magnetic field for the other. And the cross product electric field give magnetic field, and cross product magnetic field give electric field because the two of them are perpendicular to each other. And like the equal to zero has to do with the fact that if the charge, if you take in X or Y or Z direction of a charge that is not moving, then that there's no magnetic field associated with that. All right, if it is not moving, then there is no magnetic field, and if there's only an electric field associated with it. But I digress. I have been digressing for about 27 minutes. So let me get back to what into the territory. This is like me going, well, Jamaicans don't have no natural enemies. So Jamaicans' only natural enemies are Jamaicans. But this is like an Israeli going walking into Palestine. All right. I'm going to go back to what it was that we were doing. Sorry, I went too far out. So we'll go back to make sure I say, so I'll leave in this alone for the time. No, I'll leave in this alone, period. So let me go back to run back into my territory. So I was just trying to make a context. Why is it that we're doing all of this curl and divergence and gradient? All right, so I had a problem listed here. By the way, you know all of these coming about Superman and Aquaman and Flash.
Yes, sir. All in the DC universe.
Okay, so you know, like Flash, you know what Flash can, this Flash can go through the wall, right?
Yeah, in phase through by going at a certain speed and vibrating in molecules. Yeah, I want to know
No learn about them thing then, sir. No learn about them thing.
simple physics.
Yeah.
Yeah?
Is deep physics going to Flash, you know? Flash said that physics said that if the wave is of the wavelength of the other wavelength of the gap, then you can go through. So because it's moving so fast, then the wavelength.
In resonating body at a
therefore,
high frequency to match a wall. Some can feel through.
Right. You can go through the wall. If you go fast enough, you can go through the wall. And Einstein said if you go fast enough, you can catch up with time and make time start go back. because for the using the hypothesis, again I'm straight, but let me straight a little bit before we work out the problem. Using the hypothesis that if what you are seeing now, you are seeing no, is because light traveled to you. So the light leave the person and come into you, so you can see the event now. So his hypothesis is that if, let us say the thing happened in 1507, that light is, the light from that event is still traveling throughout space. It is not diminishing. So if you can go fast enough to catch up back with it. Just like if a bus leave you, you're going to catch a bus and the bus leave, and if you can run fast enough, you catch up back with the bus. So if the light leave the event, people who were at the event can't see the event because they're instantaneous. But if the light is still traveling, so what I'm saying is that if you can catch up with the light and go faster than the light, then you can see what was happening in 1507 and go way, 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 way back in time as long as you can catch up with all the light that was in it. So back to what we were talking about. All right, so the whole entire thing about electromagnetic space is a kind of fascinating thought experiment. But we want to find curl F and the not so fascinating thing. So our curl I, J, K, 2 x squared y z squared. What we say? All right, so if we were to find the curl, it would be derivative with respect to y, derivative with respect to z of x, y, z, x cubed y squared z minus j x z 2x squared y z squared x cubed y squared z plus k. All right, so we are going to differentiate this term here with respect to y and leave the others alone. We're going to differentiate y, we're going to get 2y, so this is x cubed 2y z minus, where we differentiate the z is going to be x, y, and 1 is minus j, differentiated with respect to x. So this is 3x squared, y squared, z. We leave the rest of them alone. And we're differentiating with respect to z. So this is minus 2x squared, y, 2z, plus k, x, y, z, minus the differentiate with respect to y. So that's 2x squared, 1, z squared. So this is, can put the I where we normally see it now. So this is going to be 2x cubed yz minus xy I 3x squared y squared z minus 2 to 4, 4x squared yz j plus yz minus 2x squared z squared. Oh, and the explanation just come back.
Sir, I have a question to ask. I just want to clear up some confusion. Right? The equation, the cross product, right? Where you have up right now, right? For the partial x, partial y, and partial z, where you get the figures from? I'm assuming that you partially differentiate this from the main equation. No, I know that, say I have that down there. But the figure below the I, j, and the k, right?
This?
Yes, where you got those?
All right. So now,
Where
let me write it bigger. So use the first one, y, z, x, y, z, x cubed, y squared, z. For example,
Yes,
that.
sir.
Now, remember the cross product,
I understand the cross.
when you find it,
I understand the cross product, sir. I understand that step. Is for the partial y part and the partial
the
z
one,
part, where the values come for that, where you partially where you differentiate partially.
so now,
Which value you link them to?
As in,
this
yeah,
here,
wait.
All right, we realize say
you're taking this here and differentiating this one,
which one you differentiating.
and you're taking this here and differentiating this one down here.
Okay.
So,
So
you're taking z and differentiating
oh, so you're taking z of that.
respect to z, the
Oh,
one that is down there.
so the one them crossing with, that's the part, that's what the one you differentiate with. And all right, thanks, sir. I mean, I wonder where, you get the values and that confused me and that trouble me. But I clear up everything now, sir.
All right.
Answer my questions.
All right. So we just try something again. If you have a charge Q and then you surround it by a volume, or it is surrounded by a cube of radius R. That's Gauss law say E is equal to 4 pi epsilon naught R squared. That the strength of the electric field, this is the formula for the strength of the electric field at a distance R away from a point charge Q. Oh, but the volume of the point charge is this. If I differentiate this volume, then I get 4 pi R squared. So what he was saying is that E dot if you take the dot product of E times the volume, you're going to get Q over epsilon naught. So what he had used originally was this. This is the formula that they had for they got from the field strength. So if you take the dot product, if you differentiate E and then you differentiate the volume or the area surrounding, then you'll be able to get the charge divided by epsilon naught. And then now, it was also using the fact that if you for the magnetic field, you don't have any. So let me leave that there. So this represents the derivative of volume. So if you surround that charge, when you differentiate the volume, then you're going to get Q over epsilon. That you end up with those things. So Maxwell's 4 laws just trying to capture the law for Gauss's law or the law for Coulomb's law transferred into Gauss's law. And then the other law is the one that says force is equal to Ki1 I2 over R. I don't know if you know that one. Anyway, you see, me come back to it. Sorry, I digress. Will the jury please disregard those last statements and
Do your thing, sir. Do your
let us
thing.
find the divergence. The divergence. All right, so now the divergence we said was a dot product, but the dot product manifests itself as you can put in I, this is J. So well, that was 2x squared y squared, 2x squared yz squared. X, Y, Z, J. for x cubed y squared z. All right, so what we're saying is that we're taking the derivative, we're going to take the derivative of this with respect to x. So we differentiate that. This is going to give me 4x, and we'll put back everything y z squared I. And then this one, we're going to, the second term, we're going to differentiate with respect to y, so that's going to give me plus x times 1 times z j. And the third one, we're going to differentiate with respect to z. We're differentiate to get z, we get 1, so that's 4x cubed y squared. So that's 4x yz squared I plus xzj plus 4x cubed y squared. Okay.
So I'm like, well, I want to do straightforward.
All right.
Straightforward, not complicated.
The divergence is straightforward.
Sir, second to last line, second element, what? 4x y z squared I plus. Oh man, I want to name it.
X1
before the x. What is
X1
extra plus sign or something?
X.
Just say we differentiate.
Oh, that's a 1x plus sign.
So I'm talking about the sign before the X. Yeah, that.
Oh. You need to come up. All right. So we stop in here for today. Next class we need to discuss a few housekeeping matters, and we're going to ask you to do the first warm-up test. Make we see what is going on here, and then we will proceed.
Oh, you mean we're gonna do the warm-up test in the next class?
No.
That's what you mean? Oh.
No. No, we're not. I'm going to do the warm-up test next class. We're going to go through an exercise, and after we do the warm-up test and the other two tests, then we're going to talk about partial differentiation.
Okay, sir.
Not partial differentiation, partial differential equation.
All right, boss.
All right. So we're going to stop here for tonight.
Oh, so
Here. Oh, Shane, you're not supposed to type that before we do the test them.
Wait, say that again, sir. Where's the moment?
You're not supposed to type that before you do the test them. It's after you get your grade.
Wait, what am I supposed to type, sir?
Oh,
I thought we messaged you yesterday and I chat him just for see it first.
Oh, what Mr. Nerd mode? No, sir, that's
how
what
not what to move with him.
Oh, I thought we'll flash through. You know, flash talk about a whole pop physics. So it's cool that move like flash through. Remember everything.
Flash is pure physics. Oh.
Yeah. So if school was like this, you know, remember
right.
everything. You get me?
Okay.
Yes, you need to offer more theoretical physics courses, yes, sir.
Oh. Well, that too. But anyhow, that discussion for another day. All right. So we stop in here. So Wednesday, Thursday. Yeah, all right.
Wednesday. Oh, Thursday.
Wednesday for some and Thursday for rest.
Yes, sir.
All
Sir,
right.
you have your Friday class we're gone, sir.
Did you record it?
Friday or Tuesday class because when we come back from Mobile,
Well, Friday,
sir.
Friday we're going back over the same thing that we do already.
In the lab.
We're going go back. Yeah.
Oh, true. Last week when I come back on Mobile after I come out Kingston for the lab, I never have my internet till Saturday.
Mm.
So, well, that's